Hello. So in this video, we're going to explore three different types of probability distribution. So we have probability distribution, and in this course, we actually look at three different ones. The first one is normal distribution, and sometimes they also know it as Gaussian distribution. All right, so this Gauss name actually is derived from this German mathematician named Gauss himself. In fact, in the later part of the course, you're going to look at Gauss' law. And the second one is actually binomial distribution. And the third one would be Poisson distribution. So we're going to explore how these three are different from one another. And Poisson distribution actually was this named after this French mathematician. Therefore, the special pronunciation for it. So if we look at, let's first look at normal distribution. So if we look at normal distribution, right, I think everyone can sort of relate to this pretty easily. So for example, actually in day-to-day life, we actually see a lot of these or sometimes without us realizing it. So an example would be when you go to a shop and then you notice that everyone else is of for example 6'5" and above, then of course to you that would be kind of weird, because you know that on average our height is going around like probably like 5'10" on average probably. So in this case, the judgment that you actually make would be what we know as normal distribution, because you know that on average people would normally be of a certain height. Another example would be like shoe size, body temperature, IQ score. So normal distribution is actually part of the most common distribution that we know of, and I am sure another one that you can relate to is probably the marks of your exam usually. So this actually applies to a population of stuff. All right, and if we look at normal distribution, we actually have this bell curve here that you see. All right, and of course, let me just draw this out for you. And there are a few properties of normal distribution. Of course, first, you do know that the first property is that it's actually of symmetrical. All right, try to draw it as symmetrical as I can. And of course, the peak of this curve here actually would indicate the mean. All right, and the mean is actually given by this mu here. And of course, for example, like if we look at the example earlier, we can have a normal distribution of this form for the height of people, and then we can also have another different kind of normal distribution. Say this is another one, and this actually applies to probably shoe size. So you can see that the width of the curve could be different. So actually, if you look at it, the wider the width of the curve, for example, this one here is actually bigger than this. So the higher the width of the curve, it actually indicates higher standard deviation. Because standard deviation, if you remember from what we learned in the previous class, standard deviation basically also is a square root of variance, and variance actually measures the dispersion of your results in relative to your mean, right, or your expected value. And so the first property would be the peak, indicating the mean, and then second one being the higher the width, the higher the standard deviation. The third one being symmetrical, all normal distribution curve is symmetrical. And of course, if you remember from the previous class, we learned something on PDF, probability density function, and you remember that the area under the curve would then be equivalent to 1. So that's part of the things that you would actually know of when it comes to normal distribution. So again, when it comes to normal distribution, there ought to be a way for us to actually calculate the data, right? So for example, the first one earlier we talked about height, and then the second one we actually have like probably shoe size. Maybe the fourth one will be marks of exam. So while each of these actually represents a normal distribution, but it actually has different kind of values or average to it. So when it comes to us calculating it, that ought to be a standardized normal distribution. All right. So, and this standardized normal distribution is slightly different, which means we actually take all these graphs and transform it into a standardized curve that we can use to calculate all the data across that actually applies to normal distribution curve. So let's see. This is standardized normal distribution curve, and what it actually has is also a standardized normal score. All right, and we actually call this the z-score. So what happens is that the mathematicians and experts actually came up with a certain formula which represents the curve of this normal distribution, and they actually transform it into a certain formula. All right, so we say that x actually has a Gaussian or normal distribution x if it actually complies to this. So this is the representation of it, where you have mu and sigma square. If you remember, this mu here is actually the mean, and then this sigma square here actually represents the variance, because if you remember, sigma itself is standard deviation. But of course, if we're talking about standard normal distribution, right, then the property goes as such that your mu will actually be 0, and which means the average of your data population will be 0, and then this will be 1. The standard deviation would be 1. All right, and of course when it comes to us computing data from standard deviation for normal distribution curve, right? So we actually have a way of computing it. So we go by, for example, computing the probability of x in between this a and b value for my x abiding to my normal distribution curve of mu and sigma square would then, if will then go by my z-score of x minus mu over sigma. So this is actually the mean, and this is actually the standard deviation. All right, and this applies to my normal distribution n, which is given by 0, 1. So sometimes in questions you might not be able to get it in text form of what the mean or the standard deviation or variance is. So see to that you can look at what they actually represent over here, because you know that this actually indicates the mu, and this actually indicates the variance. Yeah, so remember this part here. And then so let's go to an example. All right, so say if we are looking at IQ scores. All right, and this IQ score actually follows a normal distribution in which my mean or the average goes by 100, and then I have a standard deviation of 15. All right, so if I choose someone at random, what's the probability of any person who's randomly picked that actually has IQ of more than 110. All right, so let's look at this one here. So remember earlier we actually mentioned that for questions like this, we would need to look at this value here, because this value here is our x value, and in order for us to solve this using the standard normal distribution curve, because why, we actually have the z table. So just very briefly, each of you now should be quite familiar with a z table. So basically you always see that at the top of the table you will see a normal distribution curve, and then do look out for the area that is shaded, because if you see that it is shaded to the right side, it basically means that the value that you have in the table are actually referring to values or areas of the area going to the right hand side of the curve. Similarly, there could also be z table in which you can see that on top of the table you see that the graph actually is shaded to the left. So this actually means that the value that you see actually represents the area or the probability of your graph looking to the left hand side. So these are some tips that you might want to be very careful of. So for example, let's see that as of now I am looking at a graph, a z table of my graph looking on the right, to the right side. Okay, so the first thing that I would like to do is to get my z score. As we know, we want to find the probability of IQ of the person being or having more than 110 in score. So the first step, you know that we go by this x minus mu over sigma. So be very familiar with the term. So my x here is actually 110 minus my mu is actually 100, and my sigma is actually 15, out of which will lead me to 0.67. So now when I look at the table, all right, it means that I will need to look at, so somewhere in the table here, this could be 0.67. And then if I'm looking at z table that has its area shaded to the right hand side, then it means that we are actually looking at exactly it. We want to look at the probability of my z, which is more than 0.67, right? So because if you look at the 110 earlier, you would not be able to get this value in the standard normal distribution curve. That's why the first step is to change it to the z score. And after you have got the z score, you look at the equality term here. In this case, we're looking for bigger than value. And if we are looking at score or table with area shaded to the right, then we basically just look at we look for 0.67 at the table, from the table, the z table, and that will actually give me a value of 0.2514. all right, so this is pretty much simple. So if let's say now I want to find IQ of less than 700, all right, while looking at the same table. So again, what do? The first step is to change it to the z value, right? So how I get my z score, basically I take 700 minus 100, yeah, and then I divide by 15, all right, and I get -2. And see to that I do not see a negative value from the z table. All right, so it really depends on what kind of z table you have. That's why it is important for us to know the properties of my normal distribution curve. So remember earlier we actually talked about the property, one of which being symmetrical. So basically what this means is that if I have a z score of 2, the probability of my z more than 2 will actually be the same as the probability of my z less than negative 2. The center here will actually be the mu itself. Alright? So in this case, as long as we understand the property itself, from here, even though I do not have negative 2 from in the table, so I can actually look for 2. Alright, because I know that based on the symmetrical property, the probability will actually be the same. So in this case, my probability of z less than negative 2 would be of a certain value, and after you have checked it, it will give you 0.0228. All right, so again, in terms of calculating data using normal distribution curve, the first one is always to change your z-score to get the z-score. Usually, just in case you're wondering what this z actually means, z basically means how many standard deviation away from the mean. All right, so that's a representation of what the z-score is about. So be very careful of what you want to find, and just know that of course you have your normal distribution curve, and since it's symmetry, so basically half of this is actually 0.5 in its total probability and the remaining 0.5. So you want to play around with the symmetrical part when it comes to values that involve negative or positive. All right, so that is something on normal distribution. So let's look at the second one. The second one is actually on binomial distribution. Okay, so for binomial distribution, it actually indicates or describes behavior. All right, behavior of your, say, your count variable. So you actually have a certain variable x, right? And it's usually of experiments with common features, usually independent outcomes. All right, that has either two different outcomes. So in this case, it's a yes or no. For example, if let me give you some example of what binomial distribution looks like. So for example, if you toss a coin for 100 times, what do you get? Each time you toss it, you either get a head or a tail. Yeah? And then, or if you want to check a batch of transistor, yeah, you want to check a batch of transistor and you want to see whether it is actually functional or not, or in this case it's faulty or not. So you can see that for binomial, usually it involves two different possible outcomes, and just for the sake of consistency, since just now I have indicated x for normal distribution, I'm just going to indicate this as y here. So for the event of y, which follows by binomial distribution, is actually indicated by my n and my p. All right, so my n and my p is given by this formula over here. So note that earlier in normal distribution, you get a bell curve, right? So bell curve itself, as you can see, it's a continuous distribution, correct? So for binomial, the second and the third one that we're going to discuss, you will notice that actually if I am going to draw out, and in this case, I'm not saying it as probability density function anymore. If you still remember what it is, we actually call this the PMF, probability mass function, but this is just a representation of it. So it is given by this formula here. All right, the P of my y, in this case y is just the event itself, all right, of x, is given by n x, p of x, q of n minus x. All right. So in this case, we can actually derive this further, because for normal distribution, what you have is transforming it into the z-score, right? So if you have binomial distribution, this is the formula that you look out for. And of course, this curve here is actually given by the y-axis is actually your py of your x, right? And this is your binomial curve. So of course, I would like to touch a little bit on the expected value, because you know that for the normal distribution one earlier is exactly the same, right? For normal distribution, your expected value is mu and your variance is basically your sigma square. In this case, for binomial distribution, it is actually given by NP, all right? Whereas the variance of Y is actually NPQ. So you see that there are like a few variables here. So P here is basically like the success rate that we look at, and Q is basically 1 minus P. Is actually the equivalent representation, and of course n is just the number of the trial and so on. Let's just look at examples so that it's easier for us to understand this. But before that, this is actually also represented as n factorial, x factorial, n minus x factorial, p power of x, and this q here, as what I mentioned earlier, is actually 1 minus p, and is n minus x. All right. So let's look at example. All right. This is p here earlier is the probability of success. Of course, the q is just basically 1 minus p. All right. The x here is just our count variable. So for example, if I'm looking at a test, all right, I'm looking at, okay, we have tested a certain number of wells, all right, and we found out that 20% of the wells, all right, are contaminated. So find the probability in the random sample of 10 wells, all right, that 2 wells are actually contaminated. All right, so this just as some example of what you could see or come across when it comes to binomial. So you can see the outcome is basically contaminated or not contaminated, right? And so how do we get this looking at the formula here? So it basically means that these 2 here, right? This 2 here is actually so this 2 here is actually my x. It's always important to first identify what it is, and what we want to find is probability of 2 wells being contaminated. And it's, what do we have so far? We have 20% of the well that is contaminated. So this actually is our P. All right. So if I am going to write this down, it will be P of 2, right? Because I'm looking at probability of 2 wells being contaminated. So being contaminated gives, contamination rate gives me 20%. So if I am going to write it down exactly as the above one, the formula above, so it gives me out of 10 wells, I want to find probability of 2 wells being contaminated. And how many percent is contaminated? 0.2 is contaminated. All right. And then my x, I have identified it as 2, right? And then my q. Q basically is 1 minus p. All right. So basically this sort of like indicates the part where the wells that are not contaminated. So 1 minus 0.2, 1 minus p, right? So 1 minus 0.2 gives me 0.8. And then of course it's n minus x at the top part here. So n itself is 10 and x is 2, so 10 minus 2 will give me 8. See to that another way that I usually like to use to just sort of cross-check that I am writing this correctly is that your P and your Q would always sum up to 1, and so is your N and your X. So if you look at the power factor for your P and your Q, it usually should add up to the number of 10 here, which is my N. Alright, so 2 plus 8 is actually 10. And of course, in exam, or you might see certain formula that they actually show it in this way, but you should also know that this actually translates to my 10 factorial and then 2 factorial and 10 minus 2 factorial, right? So this gives me 8 factorial. So I will get 0.2 power of 2 and 0.8 power of 8. Alright, and then you just solve it with your calculator as it is. This should give you about somewhere around 0.302. So in case where sometimes you're wondering, okay, how many decimal points I should look at, so I usually go about like 3 to 4 decimal points. But don't worry if your result is slightly different from your friends. It's just the matter of number of decimal points that you take into account when you're calculating it. So the most important one is that you understand how to calculate this. So you can see that there are two differences, right? Earlier for normal distribution. Normal distribution, you just basically transform your x value into z and then look up from the z table, which gives you the probability. And for binomial, usually you look at events with 1 or 2 outcomes, right? And it's given by the formula as you see over here. So this is on binomial distribution, and now I would like to bring you to the last part, which is Poisson distribution. All right, so this is the third part on Poisson distribution, name of the French mathematician. So again, similar with our binomial distribution, Poisson distribution is also discrete. All right. So this usually models for frequency of event, for example, all right, and sometimes it's probability of a given number of events, but it actually has a fixed interval some sort. And what's the characteristic of Poisson distribution? Usually your experiment consists of counting events in a particular unit, all right? So it can be of time, area, volume, and then the probability of that event occurring in the given unit is the same for every unit, all right? So that's the second one. Probability that an event occurs in a given unit is the same for every unit, all right? So the unit is consistent here. Another one is, of course, the number of events that occur in one unit is actually independent of number of events occurring in other units. So the independence part. All right. But again, these are some examples of what it is on the characteristic of Poisson distribution. And now for Poisson distribution, all right, we see that X has Poisson distribution, all right, with the parameter of lambda, all right. How we represent this? We usually represent it as x, then Poisson, and then lambda, all right. And what is the formula that we look at here? Over here, we actually look at P of k equals to my lambda of k e to the power of negative lambda over k factorial. All right, so this k here is basically our count variable, and sometimes it's pretty easy to actually indicate to tell that it is a Poisson distribution, because usually this lambda here is actually the parameter for my Poisson, and it actually indicates average number of events per unit. Remember, we talk about a specific unit here, and usually when you see that a certain situation actually gives you average number of the certain event or a certain unit, then it's high chance that we're actually using Poisson distribution. All right, so if of course, if I just sort of like just sketch out a graph for you, this is basically my P of k. So if you remember, we just go by the basics. So the expected value of my event x here for a Poisson distribution is given by this parameter lambda, and my variance of my x is also lambda. So again, let's look at some example of what would actually pass as a Poisson distribution. Okay, so for example, I have customers arriving at a counter. All right, so they buy something and they go to the counter to the cashier or counter to make their payment. All right, suppose that we actually have customers that arrive at a counter with average rate of 6 per minute. All right, so we have 6 customers going to the cash counter per minute. All right, and the random variable customer arrival here has Poisson distribution. So calculate that probability that in a minute that there's a possibility of 1 arrival. All right, so in other words, we're going to look at probability that there's 1 arrival. All right, so in this case then my k is actually equivalent to 1, correct? And then again, the average rate, remember the term average and all that, so this actually indicates my lambda, right? So this itself here is actually my lambda. I have my lambda, which is 6. All right, and then I want to look at a probability of 1 arrival. So I have P of 1, and then this is actually 6, which is my lambda. My lambda is 6 power of k. My k is actually 1, so 6 power of 1. And then e exponential to the power of negative lambda. So in this case, this is negative 6. All right, and then over k factorial. So in this case, my k is 1 factorial, basically just gives me 1. And of course, when you look into your calculator and you type all this, you will be getting around 0.015. All right, so this would be the answer for it. Okay, so if we just want to recap everything from whatever that we looked at earlier, so first you have normal distribution. For normal distribution, you always want to look at the x score. All right, you want to transform it into the z score, and the z score is given by, if you remember, that will be your x minus mu over sigma. So do know that for standard deviation, for standard normal distribution, we always go by my normal distribution of 0 and 1, in which this is actually my mu and this is actually my standard deviation. Basically, z-score just indicates how many standard deviation away from my mean. All right, and so this is 1. For normal distribution, transform everything into the z-score and do not stop just yet. When you get the z-score, you look at what probability you would like to see, whether it's bigger than or less than and so on. And you want to be very careful with the z table. You want to be sure that it is actually either looking to the right hand side or to the left hand side, and then you just perform your calculation accordingly. That's for normal distribution. So do remember that for standard normal distribution, that this actually applies to population mean, and this applies to population standard deviation. So that is for normal distribution. For binomial distribution, basically we have two set of outcomes: yes or no, does it rain or does it not, um, is the transistor faulty or not. So usually it goes by n x and then p power of x and then q of power of n minus x. So do remember that my q is actually 1 minus p, and another way is also to cross check that your p and q will usually add up to 1, and this your x plus n minus x will then of course go back to the sum of n. All right, so that is for binomial distribution. For Poisson distribution, usually you deal with the lambda and you see the average. So for the average and all that, it goes by this formula of pk equals to your lambda power of k exponential power negative lambda over k. All right, this is your count variable as from the example that you saw earlier, and this lambda here will then be the average number of event. So chances are when you say average rate of something, then that statistical question actually refers to Poisson distribution. So I hope you are clear with these three, and it will definitely help when it comes to reading case scenarios and deciding which distribution you should follow. All right.